Vectors can also interact with each other through addition and subtraction, among other things. Suppose we have two vectors, u and v, and we're first going to conceptualize addition geometrically. So with geometric addition, we can consider something called a parallelogram law or something called the triangle law. The parallelogram law says take the vector v and the vector u and orient them so that their tails are at the same point. And the parallelogram that is formed by basically closing up the shape has a diagonal. That diagonal is going to be the sum of u and v. And you'll see here that I've written u plus v with the arrow over the entire u plus v. It actually wouldn't really matter if we wrote it as the vector u plus the vector v. But as it's a new vector here, I'm denoting it with the arrow over the both. I don't usually say over the both. That was a little weird, but we're going to move on. The triangle law. And I noticed I forgot to label u and v in the first picture, but I've done it now. Here we've got u and v, and what we've done is we've taken the tail of v and placed it at the head of u. Now the vector that is formed by going from the tail of u to the head of v is also the vector u plus v. And here notice since we started at u and then traversed all the way to u's head and then v's tail all the way to v's head, u plus v will have the direction that points towards the direction of v's head. It works out similarly for uv, that is the head of uv will point roughly in the directions, like the combined direction, if you will, of u and v. It's just easier to see, I think, using the triangle law, that you're using all of u and then all of v, and that gives you your new vector. Of course, it wouldn't matter actually if we started with u or started with v. So I'm just going to do a quick little rearranging bit here and say if we started with v and then put u at the head of v and then connected the tail of v to the head of u, we'd still end up with the same vector. And what we've just described is that the vector addition v plus u results in the same vector as u plus v. In other words, vector addition is commutative. And as you can see, the vector that resulted from using the triangle law is the same as the vector that results from using the parallelogram law. It shouldn't really be a surprise because they're intended to represent the same result. While we're at it, we can talk about geometric subtraction. Starting with the same two vectors u and v, if we want to subtract v from u or u from v, well, subtraction is not going to be commutative, so we have to decide which goes first. One way to conceptualize subtraction is, say, if I'm considering u minus v, the vector u, and then bringing in the negative of the vector v, same magnitude, but it points in the opposite direction. And using the triangle law, I would start at the tail of u, end up with the head of v, and the result would be the vector u minus v. Another triangular depiction of vector subtraction is a little bit tougher to grasp, but can be useful in certain contexts. And what we would do in this case is put the tails of u and v at the same location here, and starting at the head of v, drawing a vector in the that ends at the head of u is going to be the vector u minus v. And I've written it as two different vectors this time, u vector minus v vector. And the reason for that is because I think the easiest way to conceptualize why this actually works is if we were to take the vector v and add to it what we just came up with, u minus v, then we would see that the v's end up subtracting out. The result is u, and that's exactly what we would expect. I'll further appeal to the aspect that here the u minus v that we developed in the second iteration here has the same magnitude and direction as the vector u minus v that we did the first way. So here, to finish this off, this equals the vector u. And we can combine the concepts of scalar multiplication and addition and subtraction by, if we think of like, say, 2u plus 3v, geometrically what I would do is I would draw 2 copies of u and 3 copies of v, and then perform addition in the way we know we just saw, or likewise 2u minus 3v. We scale the vectors first and then perform the addition or subtraction as directed. And those are geometric views of addition and subtraction. We can consider algebraic addition as well. And I'll throw in subtraction as well. Algebraic addition and subtraction are performed component by component. That is to say, if u is equal to, we'll say a1, a2, a3, and v is equal to b1, b2, b3, then the vector u plus v can be obtained by adding a1, b1, and then a2, b2. Oh, that's supposed to be adding. And then a3 plus b3 would be the third component. And before we move on to the next concept here, I'm going to give you a screenshot actually of the textbook here. And it's properties of vectors. And I'm not going to go through all of this here, but one of the things we can see is a plus b is equal to b plus a. So that's the commutative property. But one of the things I want to point out here is the notation in the textbook. A, B, and C here are in bold and non-italicized. And we're saying vectors in V sub n, just n space, not tied to any particular dimension. C and D are not in bold and they are italicized. And that's the way our textbook author is going to distinguish a vector from a scalar. With us, we're going to draw it with little arrows. But our textbook author is going to draw it in bold. So this a plus 0 here equals a. It's saying the vector a plus the 0 vector is equal to a. And then we see we have, some distributive properties here related to addition and scalar multiplication, associative property for addition, and then also scalar multiplication. I leave it to you to review these properties.